Hi guys, welcome to the temperature tutorial. The main point of this tutorial is just to help you understand the difference between temperature and heat, and then also to talk about the different temperature scales. The difference between temperature and heat is very, very hard to explain and very hard to understand. So you're going to have to work pretty hard right now to wrap your brain around this. Look at the definitions and you can right away see that temperature and heat have very similar sounding definitions, and this makes it confusing for people when they try to figure out the difference. So let's look at them one at a time. Temperature is actually a speed. It's how quickly the particles of a substance are moving. We measure that with a thermometer, and here's how this is what that looks like. We're taking advantage of the property of thermal expansion. So I'm going to draw my thermometer in a before and after state. Kind of crude little drawings here. And what I'm going to do, I'm going to add some particles. So I have a liquid down here. We'll color it red just for argument's sake. And let's say we'll do 6 particles. Oh, why not? Let's do 7. So we have 7 particles of a liquid, and they're rotating around each other, right? So they have this kind of motion. Now, let's say that I speed those particles up. To do that, I'm going to need heat, which is a form of energy. So I give them heat energy, and as a result, the particles move faster. What do they do as a result of moving faster? They spread apart. So the same 7 particles need more room. So some of them go up into the thermometer tube, and that's what we read as a temperature. We just have to put numbers on here to figure out how high up this liquid has traveled as a result of its expansion. And remember, what caused it to expand was its speed, was the speed that the particles were moving at. All right, now let's go to heat. Heat is what causes the particles to speed up. It's a form of energy, specifically kinetic energy, which means energy of motion. And that kinetic energy is what allows the particles to move more quickly. Remember what the definition of energy is. Energy is anything that can cause changes in matter. Compare that definition to the definition of matter itself. Matter has to take up space and resist being moved. Heat doesn't do either of those things. I can't fill up a container with heat. I can't fill a balloon with heat. I can't fill anything with heat. And I don't find that heat resists being moved. What's confusing, though, is that if you have heat, you have to have particles. You cannot have heat unless there are particles, because what heat actually is the motion of your particles. So no particles, no motion. Now, if you're in outer space, it's really, really cold because there are no particles. There's energy out there. There's energy in the form of light, which is traveling from the sun towards the earth and in all directions from the sun. So there's plenty of energy in outer space, but it's not heat energy because there are no particles for that energy to move. So heat energy is moving particles, but temperature is the speed the particles are moving at. So they're related to each other. You need heat in order to change the temperature. However, temperature is not a measure of heat. Heat is a form of energy. We measure it in units called kilojoules, kJ. Temperature is generally measured in degrees, either Fahrenheit or Celsius. And then we're going to learn another scale called Kelvin, which is not actually measured in degrees usually. And that's what the rest of this tutorial is about, these 3 temperature scales. All right, here's a comparison of Fahrenheit, Celsius, and Kelvin. All 3 of them use the same kind of thermometer, but they were invented at different times by different people. So I gave you a reading that goes into the specific details of this, but I'm going to give you the gist of the story right here. We start out in around 1714 or so with Daniel Fahrenheit. Daniel Fahrenheit created the first modern thermometer. There were thermometers before that, but they used a totally different technique. What Fahrenheit did was he put mercury, which is actually a silvery liquid, in the bottom of his bulb, and he decided it was time to finally put a scale on the thermometer. Before that, there were no numbers up the side of the thermometer. The thermometer just told you whether something was getting hotter or colder by whether or not the particles of the substance in it were going up or down the tube. But he decided he wanted to actually be able to measure differences between the temperature of one thing and the temperature of another thing. And in order to do that, he had to create a scale. There are lots of different things he could have done. He could have just, divided his thermometer into equal parts. And that's probably what he should have done. But instead, what he did was he based his thermometer scale off of something very familiar to him. He based it off of a circle. Now, you might remember from math class that a circle is made up of degrees. Specifically, if you go in a complete circle, you travel 360 degrees. Half a circle, therefore, is 180 degrees. Whoops. And you might have noticed that a protractor has 180 degrees on it. 180 over here, 0 over here. And protractors measure angles. This was a very familiar concept to Daniel Fahrenheit, and so he was thinking of a circle when he invented his scale, which made him think of 180 degrees as the distance from one end of a line to the other end of a line. And so, because of that, he decided not to break his thermometer into 100 equal parts from top to bottom, but to break it into 180, which is weird. But that's what he did, so we kind of got stuck with it. Not only that, but he also decided that he was going to make the bottom and top of his scale the freezing and boiling points of water, because to him, those were the coldest and hottest temperatures that he was familiar with. So what he did was he started with 0 for the temperature that water would freeze at, and 180 as the temperature that water would boil at. But very soon after he decided that, something happened that created a problem. He discovered something colder than ice. Specifically, he discovered ice cream. Well, he didn't discover it, but it was being discovered at the time. Ice cream is made by adding, or it used to be made, by adding salt to ice water to cool the ice water down to below the temperature that water freezes at, because you need it to be actually colder than that in order to freeze cream, which is what ice cream is, frozen cream. So, once he realized this, he found that the freezing temperature of ice with salt in it was much lower, and that meant that he couldn't make 0 be the freezing point of water. It had to now be the freezing point of his ice water solution. And that moved the freezing point of water up to 32 degrees, which moved the boiling point of water up to 212 degrees. Now, hopefully you're beginning to realize right about now that this is a problem. This is a very ugly scale. By ugly, I mean these are the kinds of numbers that human beings don't like. We like nice round numbers. They're easier to remember. They're easier to work with. We like things that use the base 10 scale so that it's easy to divide and multiply by tens. So this was a really ugly scale, and it wasn't very long before somebody else came along, a guy named Anders Celsius, and he said, you know what, I don't like the Fahrenheit scale. I'm going to recreate the scale from 0 to 100. And that's what he did. He decided he'd make water 0 for the freezing point and the boiling point of water 100 degrees. And then he just divided up his thermometer into 100 equal parts between that 0 and that 100. And he called that scale the centigrade scale because centi means 1/100th and grade as in gradations or graduations, little pieces. The centigrade scale was much easier for people to understand. It was more convenient. It was easier to remember the boiling and freezing points of water, and that was terrific. But then, in the mid-1800s, a guy named Kelvin decided that now that we understood what temperature really was, that it was a speed, he said, you know what, we can't have negative numbers. Look at all these negative numbers we have with Celsius and Fahrenheit. You can't have a negative speed. Something can't be going slower than not moving. So he said, you know what, we need to redesign our temperature scale, making 0 be the absolute lowest temperature you can reach. And this is where we get the concept of absolute 0. This is the temperature at which, in theory, all particles would stop moving. If we could remove all the energy from the universe, the particles would stop moving. We can't do that, but in theory, if we could, it should happen at this temperature on the Celsius scale, negative 273 degrees Celsius, and this temperature on the Fahrenheit scale, negative 460. And when you're in outer space, you're around negative 450 or so degrees Fahrenheit in some parts of space, and so it's really, really, really cold. So the Kelvin scale got rid of the word degrees. You notice that Celsius took the word degrees from Fahrenheit, even though we were no longer talking about a circle. Kelvin dropped the word degrees. And also, Kelvin is a word that is the same when it's singular as when it's plural, which is like the word deer, right? If you have 1 deer, you write it like that. If you have 10 deer, you write it like this. You don't put an S on it. Same thing with Kelvin. You have 1 Kelvin, you have 10 Kelvin, you don't have 10 Kelvins. And you certainly don't have 10 degrees Kelvin. You might, in your travels on the internet, see degrees Kelvin written or Kelvins written, and that does happen because the internet is open to everybody and people are allowed to do whatever they want. But technically, I was taught that you say Kelvin, not Kelvins, and you don't say degrees. And that is the story of the temperature scales. Okay, see you in class.